So in this module we will continue to study Maxwell's equation. We will first begin by looking at the solution of Maxwell's equation. We will first assume that a certain solution has been given and then check whether that solution is valid or not, whether the expressions for electric and magnetic fields satisfy Maxwell's equation. If you remember, in the previous module we had actually seen a case where such a expression was not valid for Maxwell's equation. That is, it was alright for quasi-static case, but it was not valid for as Maxwell's solution of Maxwell's equation because it did not satisfy all of the Maxwell's equation. So to see the counter example for that, consider an electric field which is given having only the y component. So the y component of the electric field is given as some constant d0, okay, divided by square root of mu 0 and epsilon 0. We are considering the medium which is free space. So for free space, mu is mu 0 and epsilon is epsilon 0. So I have the y component of the electric field being some cos omega square root mu 0 epsilon 0 times x. So this is the electric field that I have. It is a cosine function in x. Okay. Now someone also has calculated magnetic field or magnetic flux density component Bz, and they have given this as minus j d0 sine, not cos, but sine of omega square root mu 0 epsilon 0 into x. Okay. You might actually question what happened to the time variations. I mean, after all, we made such a hue and cry about time variation, but time variation seems to have disappeared. The key to remember this is that time variation has not really disappeared, but time harmonic solutions, that is those E and B fields, or in all the other fields E, B, H and D fields, when they are time harmonic, then the time derivatives or the time functions can be replaced by omega, or rather j omega, and therefore time actually sort of seems to have gone away. Okay. But there is a time. So if you want to really obtain the electric field value, correct electric field value, what you have to do is you have to first convert this scalar Ey into a vector component. So here E is along y direction, and then to this Ey you need to multiply by e power j omega t and then take the real part of it. Okay. If you do that, you will actually get E, which is function of both space as well as time variables. Okay. We are not going to do this one at this point. We are going to still assume that we are in the time harmonic form, and then we will use the time harmonic Maxwell's equations to see whether these pair of solutions which someone has worked out is consistent with Maxwell's equations or not. They are solutions of Maxwell's equations or they are not solutions of Maxwell's equation. Okay. Now to perform this solution check, I have to individually check for all the Maxwell's equations. So if I start with Faraday's law, I have curl of electric field being given by minus j omega b. I do know that b field is only along z direction, so this can be written as minus j omega bz, and you are interested only in the z component of the curl of E. And what is the z component of curl of E? This would be del E y by del x minus del E x by del y. Okay, this is the z component of the curl of E. This should be equal to minus j omega bz. I hope that this change you guys understood, although this is not the proper way to write this expression because this is a vector and this is a scalar. But the point I was trying to make here is that the B field has only z component, therefore I can write down this as minus j omega bz, becomes a scalar, right. Similarly, for the curl I can have x and y components, but those components do not have any counterpart in the right hand side, so which means that those components must be 0. We do not want to bother about those. All we are interested now is only the z component of the curl of E, right, and this z component is actually given by del Ey by del x minus del Ex by del y. What are the values of electric fields that we have been given? We have been only given Ey component, Ex component is 0, and therefore this term goes away, right. So now that the term has gone, we are reduced to a simple equation del Ey by del x is equal to minus j omega Bz. What is the next step? We substitute for the corresponding values, right? What is, let us evaluate them over here so that I can see the expressions while they are on the board. So what is minus j omega Bz? So first consider the right hand side term. So minus j omega Bz will be minus j omega into minus j d0, minus and minus will become plus, j and j becomes minus. So I get minus omega d0 and nothing happens to the sine term, so it is sine of omega square root mu 0 epsilon 0 x. So if I actually get the left hand side to be exactly this one, then this Faraday's law would be satisfied. That is just one law that we are looking at. So what is left hand side? To get the left hand side I need to differentiate this Ey with respect to x. So if I differentiate Ey with respect to x, because this is cos of something into x, cos of something into x when you differentiate with respect to x becomes sine of something into x, then that something will come out of the argument, right. So the left hand side is basically d0 divided by square root of mu 0 epsilon 0. Omega square root of mu 0 epsilon 0 is something that has actually come out. Cos has become minus sine, so therefore there is a minus sign here, minus sine of omega mu 0, omega square root of mu 0 epsilon 0 into x. Clearly square root mu 0 on numerator and denominator will cancel, leaving behind minus omega d0 sine of omega square root mu 0 epsilon 0 x. This is precisely what is equal to the right hand side. So Faraday's law is satisfied. So we come to the conclusion that since left hand side and right hand side are equal, Faraday's law is satisfied. So at least out of 4 equations we have satisfied one equation. Now let us try and find out whether the divergence equations are satisfied. So first let us look at del dot D equal to 0, and D is epsilon into E, and epsilon is a constant. So this equation simply becomes del dot E is equal to 0. Is this del dot E equal to 0? Is this correct? I mean I am assuming 0 because I am assuming that the medium has no charges, right. If this turns out to be non-zero, then it means that there are some charges which we are trying to find out. So if I try to find the divergence of this, remember divergence will involve components like del E x by del x, del E y by del y, del E z by del z. Ex and Ez are 0 already, and Ey unfortunately is not even a function of y. Ey is function of x, therefore this would also be equal to 0. So we have seen that in free space del dot E is equal to 0. Well, you might say that there is no big deal out here, we already knew that, but it is gratifying in some sense to show that Gauss's law for electric field is also satisfied. That is, the solutions that someone has worked out satisfies Faraday's law, it also satisfies Gauss's law. Can it be a situation where del dot B is non-zero? Well, we do know that del dot B cannot be 0, and to test that one you look at what is del Bz by del z. Bz is a function only of x, it is not a function of z. So del Bz by del z should also be equal to 0. So clearly Gauss's law for both magnetic field as well as for electric field is also satisfied. Okay. Then remains only one other equation, which is curl of H is equal to, there is no J fields here because this is perfectly dielectric medium, there are no free conducting charges, there is no conduction current. So what you have is curl of H is equal to plus j omega epsilon E, correct, because j omega is del by del t, epsilon E is d, so this should be j omega epsilon E. Again going back to the scalar form, this is j omega epsilon, and since this is free space we have epsilon 0 and electric field is Ey. So I need to find out only the y component of this curl of H. And what is the y component of curl of H? The y component is del Hx by del z minus del hz by del x. Again hx is 0 because bx is 0 and hz is given by bz divided by mu 0, right. So del hz by del x will be 1 by mu 0 del bz by del x. So now I just need to find out what is del bz by del x. So go back to the expression over here. There is a sine of something into x, so that sine of something becomes cos of something, right. So this becomes cos of something, right, and that something will come out of the integral. So what you get here is, for the left hand side, 1 by mu 0, sorry, there is a minus j d0 omega square root mu 0 epsilon 0, which is that something that has come out, and sine has become cos, and the argument of this one is omega 0 mu 0 into square root of mu 0 epsilon 0 into omega into x. So there is a mu 0 here, there is a square root of mu 0 in the numerator, so you can rewrite this as minus j d0 omega divided by, or omega into square root of epsilon 0 by mu 0 cos of this into x, right. This is what the left hand side would suggest to you. Is this the same as the right hand side? Well, what is Ey? Ey is given as d0 by square root mu 0 epsilon 0 and cos of omega square root mu 0 epsilon 0 into x, right. This was Ey. Now if I multiply this Ey by j omega epsilon 0 into Ey, that will be equal to j omega and so there is a minus sign here because this curl of h for the y component is minus del hz by del x. Therefore the left hand side will actually have a minus of minus, that becomes plus, okay. Now you have j omega epsilon 0, so multiplying by epsilon, I have one epsilon in the numerator, square root of epsilon in the denominator, so I can replace that and say this is epsilon 0 by mu 0, there is a constant d0 here and cos of omega square root mu 0 epsilon 0 into x, okay. So we have Ampere Maxwell or modified Ampere's law also satisfied. So we have satisfied all Maxwell's equation, and therefore this Ey and Bz, which is equal to minus j d0 sine of omega square root mu 0 epsilon 0 into x, is a perfectly valid solution for Maxwell's equation, okay. These are the perfectly valid time harmonic solutions. You will later see that these actually come up, this type of cos of something into x and sine of something into x would actually come up when you consider waveguides, and these are known as standing waves, okay. Whenever you have two conductors or region bounded by two conductors, then you will actually have these standing waves. So you will see this later. There is one other aspect which I want to talk about, and that is the boundary conditions. So we will be looking at two types of boundary conditions. One is for dielectric and conductor, and the other one is for dielectric and dielectric, okay. So you have dielectric 1 and dielectric 2, okay. So what are the equations that would change? The equations for integral of b dot ds is equal to 0 does not really change whether you have a dielectric or a conductor, right. So this will continue to give you the normal component bn1 must be equal to bn2. Similarly, integral of d dot ds over that closed surface would actually give rise to, is equal to the total charge enclosed, would actually give rise to dn1 minus dn2 must be equal to surface charge density, right. When will this surface charge density be present? Only when I have a conductor, right. So for a conductor, the surface charges are slightly in the inner region, so there will be some surface charge density on a small thin layer, there will be some surface charge density. However, between dielectric to dielectric, surface charge density is 0. So this would be either equal to rho s or equal to 0 depending on whether you are in a dielectric to conductor or dielectric to dielectric boundary, Okay. For the other two equations, you have integral of E dot dl being equal to integral of minus del B by del T dot ds, right. Now for this, I know that if I apply the loop onto the left hand side, I end up having E tangential 1, with some delta L, minus E tangential 2 with some delta L, that must be equal to minus del B by del T into delta L into delta W, right. Now here is where we actually have a slight problem. Previously you could simply have this term was equal to 0 and delta L we could have removed everywhere. We could still remove delta L from all sides, we will remove that one. But what would happen to minus del B by del T into delta W as delta W goes to 0? Now if del B by del T remains finite, right, if this del B by del T remains finite, then this term will actually go to 0, right. As long as this term is finite, then the product will go to 0, right. As delta omega is 0, the right hand side term will go to 0 and you are left with tangential continuity of the electric fields. Okay. This is certainly true for dielectric to dielectric. Okay. For conductors also it is true, because we do not let our fields go to infinity. Okay. We do not let the fields go to infinity because that would imply a lot of other things. Fields are always finite, continuous. Okay. That is the physical reason behind this one. Okay. So we do not have a situation where del B by del T is actually going off to infinity, and because of that reason ET1 is still equal to ET2. Okay. The other condition is that I have integral of H dot dl is equal to conduction current that is enclosed, right. So let us say I enclosed, which is conduction current, plus a term for del D by del T delta L delta W, right. Again writing the left hand side as HT1 delta L minus HT2 delta L, where delta L is the path length which we have seen in earlier modules. This seems to be sigma, right. Conduction current J, we have shown that this is equal to sigma into E sometime in one of the modules that we have already shown this, right. So this seems to be indicating that this is sigma E delta L delta W. As before, we do not want to let our del D by del T go to infinity. So as delta W goes to 0, this term will also go to 0. Okay. This is certainly true for the dielectric to dielectric, because in a dielectric to dielectric this term is anyway 0, the conduction current density is anyway 0. So this is actually 0 for dielectric to dielectric, and if you assume that the fields are finite, then the right hand side term will also be equal to 0. HT1 will be equal to HT2, tangential H components are continuous. However, when you have an ideal conductor and an ideal dielectric, right, then we can have a non-zero value for the right hand side. Even when E is finite, okay, we assume that as delta L cancels everywhere away, we assume that sigma goes off to infinity for an ideal dielectric, but the density E will also be in such a way that the product of this E into delta W goes to 0. Okay. So infinity into 0, that is a large value and a small value, can multiply with each other, so that the resultant term will be equal to some non-zero finite value. Okay. So we let sigma go to infinity for an ideal conductor and we let the electric field go to 0. So you are actually looking at a very small field multiplied by a very large conductor value. Together they will form what is called as a surface current density, okay, or sometimes called as a current sheet. Okay. So this current sheet is actually spread only over a very small layer inside the conductor, and that layer is called as the skin depth. It will only penetrate to a small layer inside, but the point here is that in a conductor to dielectric interface you can have current sheets. Okay. There will be currents on the walls of a conductor which would be varying with time. So this is the boundary conditions that I wanted to discuss. Luckily not much has changed. We could also discuss the uniqueness theorems. If you remember, we discussed uniqueness to show that the potentials of a closed region once you specify the potentials on the boundary and the charge distribution on certain surfaces, then the electric field was unique, right? Potentials were whatever that you found was unique, but you can actually do a similar uniqueness theorems not for the potentials but for the electric and magnetic fields, and you can show that if the same conditions would actually hold true. That is, once you have found a unique solution for magnetic fields and electric fields that satisfies Maxwell's equations, then those solutions are unique. Okay, you can relax that closed surface and the closed surface going to infinity criteria by making the surface open, right? You can actually extend the conditions to infinity, but provided electric field and magnetic field both decay at least as 1 by r, in the sense that Re must go to 0, Rb must go to 0. Okay, so this is the only condition that we have, and these conditions are called as radiation conditions. A discussion of uniqueness theorem for this is completely beyond the scope of this module, so we are not going to consider these conditions and the corresponding uniqueness theorems. Okay, so once you have solved Maxwell's equations and found out the electric and magnetic fields, then they are unique. Okay, except for some constants which are really not important. So we have looked at radiation condition and uniqueness theorem. Before leaving the subject of Maxwell's equation, I would like to point out one commonly asked kind of a solution in Maxwell's equation. We know that, let me just write down the Maxwell's equations for you again. Curl of electric field is minus del B by del T, right? Curl of H is equal to J plus del D by del T, del dot B is equal to 0 and del dot D is equal to 0. A frequently asked question is that, are these equations completely independent of each other, or one of those equations can be derived from the other, right? And typically we show this by considering del dot del cross E equal to 0, obviously, because divergence of electric field must be equal to 0. So for this must be equal to minus del by del T of del dot B, correct? So if you take divergence of Faraday's law on both sides, the left hand side will be equal to 0, the right hand side will be minus del by del T of del dot B. Okay, what this implies? It implies that divergence of B must be equal to 0, right, or it must be some constant, right? But if my magnetic fields have been turned on at a particular time, right, and before that the magnetic field was 0, that is the initial condition for the magnetic field B was 0 initially, then it cannot change its value, right? It cannot jump to a new value because del dot B has to remain to that constant. Okay, and if that was actually non-zero constant, then it would mean that there must be some magnetic charges that we should have found. Since neither of those two happen, right, your constant cannot change from one value to another value without having a time variation in the B field, I mean without having a variation in del dot B, or if that was already non-zero to begin with, then we should have found some magnetic charges, leads us to say that this constant cannot be anything but be equal to 0. So it seems that del dot B equal to 0 is not really an independent condition from this curl equation, because it can be derived. We have derived del dot B equal to 0 based on del cross E equals minus del B by del T equation. Now does it actually make sense to you? One school of thought tells that this should not make sense. Okay, mathematically yes, we have shown something over here, but remember we could have said del dot B equal to 0, or we could have said del dot B equal to constant. The reason why we ruled out constants anything but 0 was because we said there are no magnetic charges. Now how does one know there are no magnetic charges? Is it some rule that was given earlier? No, this is an experimental observation, right? We have so far not been able to detect any kind of magnetic charges, and therefore we will say that magnetic charges do not exist in nature, which means that the nature of the B field will have to be continuous. The B field has to continuously close upon itself. This is the physical meaning of del dot B equals 0. So it is true that mathematically you are getting del dot B equal to 0, but you are getting that 0 only because you are invoking the experimental aspect of saying that magnetic charges cannot exist in nature. Okay. So, if you blindly assume that, well, mathematics tells me that del by del t of del dot b is equal to 0 and hence del dot b equal to 0, you would be wrong, because given any function del f by del t is equal to 0, all you can conclude is that f must be some constant k. The reason k must actually go to 0 is because we have not found any magnetic charges, right, in this case. Okay. So, yes, mathematically you can show del dot b equal to 0, but that does not always follow, I mean that does not follow unless you invoke the experiment value. And moreover, this divergence equations are actually not, sorry, this del dot d equal to rho v, the divergence equations are not something that is mathematically obtained. Okay. They did not depend upon the divergence laws or something. Vector analysis was not invented until late 19th century for them to carry out this analysis and derive del dot b equal to 0. This is an experimentally observed law. Okay. So, to my mind, you should not say that this curl of E is independent or del dot b equal to 0 is not necessary and there are only two Maxwell's equations. There is a place where you are invoking experiment, and that can only mean that this cannot be considered as completely independent. Mathematically derivable only when you supplement it with experimental observation. Okay. A similar thing occurs for del cross H also. Mathematically I can take del dot del cross H and say this is equal to 0, and what it would mean is that I have del dot J plus del by del T of del dot D equal to 0, right. I know that del dot D is actually rho v, so I can write this down and say del by del T of rho v, del dot J plus del by del T of rho v is equal to 0. This is nothing but continuity equation, right. So, some actually start by assuming continuity equation and then say because continuity equation must be true, del dot D must be equal to rho v. Okay. You assume this one and then you say that del dot D equal to rho v, but this does not make any sense. This continuity equation was actually something that is postulated. You cannot get this equation. So, either you choose between using continuity equation as one of the Maxwell's equation, or you use del dot D equal to rho v as one of the Maxwell's equation. The convention is to consider del dot D equal to rho v as Maxwell's equation, because that directly talks about the fields and the charge distribution. The continuity equation is simply a conservation equation that talks about the sources themselves. So, it's kind of, the field theory separates itself out into sources which are charge distribution and current distributions, and the generated fields which are electric field, magnetic field, electric field intensity, magnetic field intensity, electric flux density and magnetic flux density. So, the source charges and currents are generating the fields, fields act on other charges and currents to produce the force effects. Okay. So, in that sense these equations are 4 Maxwell's equations, and to supplement that you have to introduce continuity equation. Okay. Otherwise you could actually generate charges without any effort, and that by way you would actually have obtained infinite amount of energy in doing so, and that would be something that is physics does not accept it.